Hello, and welcome to Exploring Axon, a podcast where we discuss Axon Framework, Axon Server, and their ecosystem. I am your host and a software developer at Axonic, Sara. Welcome to the second portion of my talk with my colleagues Sara Pellegrini and Milan Saviç. We talk distributed system, and in this portion of our conversation, we focused more on message distribution. I hope you enjoy this conversation, and let's have a listen. So let's continue with this message. So it sounds all in technically talking about it sounds pretty straightforward, and I'm sure nothing can go wrong here, right? But I'm sure something can go wrong here. So let's talk a little bit about that as well.
Yeah, Sarah, a lot can go wrong. And as we said at the beginning, when you start dealing with distributed system, you need to be prepared to everything. Basically, everything can go wrong. And one of the most common situation is that your message is not delivered properly, right? So basically, there is a component that tries to send a message, and this message and basically it do not receive any confirmation. So it may be that message doesn't reach its destination. It may be that it takes too long to be handled. Many things can happen. But a first strategy that we can use in this situation is to adopt our automatic retry mechanism. So basically the infrastructure that is responsible to dispatch this message from one component to another, anytime doesn't receive a confirmation under a certain amount of time, or if there is an explicit error, it can try again to deliver the same message once more. So this retry mechanism is one technique, is one technical solution that we can use in order to mitigate the problem of undelivered messages.
Right. And so if the retry is working, then you received your message properly. And right. So this is a good solution. So what are the others, some of the other issues that can pop up here, Milan? You were having some points there as well.
Yeah, so basically, I always get to talk about the circuit breakers because Sara Pellegrini does not like them.
Yeah, I hear she's a huge fan of it. All right, so Sara, hold your ears while Milan is talking about this. Go ahead.
So basically, in cases where retrying makes no sense, you know that server is unavailable, but there are components in your system that want to reach that information. It is really useful to fail fast there, and that's why circuit breakers are really interesting mechanisms to be implemented. What they represent is you're going to get the information that server is unavailable, and all following requests you're going to fail them right away because you know that for a certain amount of time that component is not available. You're going to fail fast, you're going to improve your performance. However, from time to time, you need to go and check whether that failed service is up again, and then you want to make the call again. You don't want to do this forever. I mean, to break the circuit forever. Yeah.
So, Sara, I have to ask, why are you not a fan of this? Because it has to break the circuit?
Because I believe that the evolving a little bit further this solution, you can achieve a lot more with a failover mechanism. So instead of failing fast only, you can basically decide to not to break the circuit, but to move basically to forward all the request that was initially addressed to the component that is not available anymore to another instance that you can start up on purpose for basically in case of the first one is not able anymore to perform its task, or maybe you can have multiple instances and just address all the loads that was directed to initially to the instance that is not working to the other instances that are already available. So this is a more powerful way to to basically implement the same concept, in my opinion.
Yeah, and get further results, which is great. Now, you both mentioned something that is, I think, is key here. So whether it's retry or failing or what have you, we want it to stop at one point, right? So we don't want this to keep going on and on and on and on. So let's talk about deadline a little bit, maybe.
Yes. So far, all solutions that we covered for messages not being delivered are technical solutions. They basically do not depend uh, on the domain that you are in. Uh, Deadlines is something that is related to the domain, especially how long you're okay with waiting for that message to be
Right.
delivered. So when you send a message, then you start your timer and say, okay, for this payment to be done, I can wait for 30 days or I can wait for 1 minute. If I do not receive the response back within that time, within that deadline, I'm just going to compensate and I'm going to say, okay, this order is going to be canceled, or I'm going to cancel this payment, whatever was the business transaction.
Mhm.
And this is where we can elevate the deadlines in our system.
Yeah, and I think what you mentioned is really important to note is that this is a business decision. And as you mentioned, with the instance of a payment, sometimes you want to receive that payment almost immediately. Say I'm at a store and I run my credit card, and if that payment doesn't come, you don't want it to retry 10 minutes and the line behind me gets longer and longer. As opposed to if this is, for instance, a utility company and you have 30 to 90 days to make your payment. And that's where that business decision comes in handy. So that was a really, really great point to make there. So now there are ways to sort of enhance this, right? This way of handling these situations. So there is another problem, Sara, that you mentioned, which we have to consider in this distributed environments, which is what could happen if it's impossible to distribute these environments and understand the reason of the failure for a particular request. So maybe let's talk about the message fails that can be reached at their destination and how we can handle those.
Yeah, because indeed, when you deal with distributed system, it's basically impossible for you to understand the real reason of a failure, right? It may be that your message arrived at its destination, but it could also be sorry that it could be that the message do not arrive at its destination, or it arrives at the destination but is not handled properly, or basically it handled properly but the confirmation cannot reach back the initial component.
Gotcha.
So it is impossible for the component that send the request to understand what happened exactly, right?
Right.
So if it doesn't receive the confirmation, everything is possible. So, in case, for example, we adopted a retry mechanism, as we explained before, it is possible that we do not receive any confirmation, but the message that we sent has been executed. So we sent again a message that it already has been executed.
So it
So,
keeps executing itself more and more each
yeah,
time. Yeah.
exactly. That's why it is very, very important that our application are able to be tolerant, to be resilient to this kind of situation. So to tolerate multiple sending of the same message. And this is something that it's the key to make our application really robust in distributed environments, because we cannot know if the message is really arrived, handled or not. So it's impossible to know that. And
Right.
the only solution we have is to basically use the design solution that allows us to be resilient to this situation.
Mhm.
One of the main solution that we can adopt is to make our messages idempotent. That is one of my favorite because it is a design solution and it's very, very powerful.
Yeah,
And
let's talk a little bit about that. What is this idempotency that we hear here and there?
yeah, idempotency is basically the property of operation, such that no matter how many times you invoke this operation, you execute this operation, you achieve always the same result. And it is really dependent of the semantic that you use for your messages. So if your messages are designed in the proper way, they can be handled in an idempotent way. We can do a very simple example here. If I want to change a number of the number of the item in my cart in the e-commerce, I can decide to send an command that require to increment this number. So increment item number containing the delta that I want to use to increment that number or decrement that number. Unfortunately, this kind of command is not idempotent, because anytime it is executed, it will produce a different result of the number of the item in the cart. Instead, if I use a different kind of semantic, so update, for example, item number containing the new value of the number of this item in the cart, no matter how many times I execute it, I will achieve the same result. So this is the kind of solution that we think that are very important in order to make your application resilient. Try to think all the time in order to implement, to design your application in such a way you have messages that can be handled in an idempotent manner.
And can we use caching in this case for our commands so that they stay in memory for a certain period of time, that it doesn't have to be executed every single time, more and more each time?
Yes, we can. Probably you mentioned a solution like the duplication, right? In this case, basically, the duplication is a technique that you can use anytime you do not have a natural identity in the context you are working on. So basically, if you cannot, for example, use technique like idempotency or identify basically the instance in such a way you can basically reapply the same command without having side effects. What you can do is to basically use the artificial identity of the message itself, caching it in order to avoid double execution of the same command.
I see, to duplicate
Yeah.
that command over and over. Gotcha. And so, Milan, in a case that we want to reject the message, how do we go about it? Let's say we just the preconditions don't compare or don't match or anything like that. How do you go about that?
Yeah, so this is a case again where we can have an identity. Order is really good example of that. So if for some reason I receive a command to confirm an order, I'm going to update my state related to that specific order with that specific order ID, and I'm going to say that this order has been confirmed. If for some reason I get confirm order with the same ID again, I'm just going to compare the states, and I'm going to see, okay, this order has been confirmed. So I'm not going to fire any order confirmed event. I'm not going to do any other actions. And it is really easy for me because this is uh, uh, something that is identifiable. Now, this is a solution that we call a compare and swap, which is very well known in language design.
Right.
There are atomic references, atomic variables that you have in a lot of languages, and there it is a technical solution, of course, right? And in our case, we said that it is a design solution because what we compare and what we swap, or what we basically in our case, it's not a swap, it is more of execution, confirming the order. I'm comparing the identity of the order, and if they match, I'm going to confirm it.
Right.
Uh, we see that as a design solution because it really depends on the domain, what we compare and what we swap.
What we're swapping. Gotcha. So you both mentioned identity in these solutions, but what if there is no identity?
In case there is no identity, unfortunately, the only solution you can adopt is the duplication, so the technical
Mhm.
one.
Gotcha.
So basically, this is a solution that you can take into consideration anytime you do not have a way, basically, to find a natural identity in the business you're trying to implement. So
Mm-hmm.
that's a solution that you can use only if you cannot find a way to use the other techniques like idempotence or comparison.
Gotcha. And so in the case of duplication, then sure, yeah, it's I guess kind of straightforward. What if then you also mentioned another possibility that the messages can be delivered in a wrong order, and how do we manage that and handle that?
So one of the cases that we can do is chaining our messages. So essentially, just knowing that I sent one message, and after that I sent a different message. They can be consumed in different order. So instead of just how to say, if my programmatic order is one, that doesn't mean that the execution order in different services is going to resemble that one that I have. So in order to overcome that, one solution can be chaining our messages. So we can say, okay, first I want to confirm this order. Once I get a response that that order has been confirmed, then I'm going to request the payment and wait for the response that the payment is confirmed. Now I'm forcing the order of message delivery. Messages, depending in our case on the network speed, network latency, can be delivered in different order, but to me it doesn't matter because with my
Right.
design, how I designed this business transaction, it is completely irrelevant what protocols are used, whether my network is slow or not. It is
Yeah.
always going to execute consistently and due to be in order with the business rules.
Gotcha. So then in this case, we're ordering the messages based on what we want to see first, executing, then next, and so on. Is this then the same as cause and effect, or is it different, Sarah?
So it's very, very similar, but slightly different. So one is so the one that Milan just explained is basically the concatenation of these messages, right? So I wait for the confirmation of the one before to send the second one, right? In causality, it's a slightly different because it's exactly basically the event that is published as a consequence of the first command that trigger the sending of the second command. So basically, it is impossible that the second command is executed before the first one because it is the event published by the execution of the first command that is the real trigger of the sending of the second command. So it is slightly different, but basically the result is the same.
Gotcha. That makes sense. So, how can we be also lenient when it comes to ordering these messages? Can you talk a little bit about that, Milan?
Yep. Uh, in this case, what you took as an example is reading the temperature from a sensor. If we receive messages in different order, if we are displaying that on the UI, it's not that big of a deal. But let's say that we have some barrier, and if temperature passes that barrier, we want to trigger a certain operation. If temperature goes below that barrier, then we want to trigger a different operation. And here, receiving messages in different order can have really, really bad influences on our system. So
Right.
one of the solutions is to be lenient about that and to, let's say, introduce a time window in which we are going to collect several measures from the sensor and we are going to apply some reduction function on those values. It could be an average, could be a mean, whatever we choose depending on our domain. And then we are going to use that reduced value to make any decision. And hopefully, I mean, even more statistically, we are going to have better decisions because our reduced value is going to have more real value than the ones that we read maybe in the wrong order. So that's how
Gotcha.
you can leverage the leniency.
Leniency. So now you did talk about various tools that we can use, the chaining the messages, cause and effect, being lenient, and so forth. So can we enforce some kind of transport protocol?
Yeah. The transport protocol is some technique that is a technique that we can use sometime, but in a limited situation. So, for example, if you want to enforce the order, if you want to guarantee the order of messages delivered from one component to another, we can use a TCP channel that guarantee the ordering of messages, and this is fine. But what happens if you want to scale up, for example, the instances of one component of the destination component, right? In this case, we have two instances, two TCP channel. It is impossible to use the protocol to guarantee the ordering of the messages. So one thing that we can do is to decide to deliver all the messages that requires to be handled sequentially to the same instance in such a way that only the messages that need to have sequentiality are taking advantage of the transport protocol. We can do that for using, for example, a consistent hashing algorithm and using as a key the key that determines this sequentiality. So basically, let's say all the messages that, for example, in our e-commerce business case, have a even customer code can be dispatched to an instance. All the messages with a node customer code can be dispatched to the other instance. In this way, we can enforce that all messages related to the same customer are handled sequentially. We don't care the order of handling two messages that are related to two different customers. So it's fine. Unfortunately, this technique, it cannot be used in all the situations. There are situations, for example, when we need to enforce the ordering of two messages that need to be necessarily sent to two different components because are two different kind of messages. There is no one single component that can handle both of them. So in this case, you cannot take advantage of the protocol, the transport protocol. So basically, yes, transport protocol and techniques like consistent hashing can help us reducing, basically alleviate the problem of message delivered in the wrong order. But yes, the best is as usual to find a proper design that is capable of solving this kind of problem at the business logic level.
Right, and that makes sense. Um, so we did a little bit ago talk about some non-functional requirements that may happen in our systems. For instance, if there's a team joining that needs to take care of a different component within the system, different, say, deployment cycle or anything like that. Can we talk about those non-functional requirements a little bit that are changing? I guess consistently or sometimes can change a little bit, Milan.
Yeah, so when non-functional requirements change, we do not want that our business logic changes. We want that our code related to the business logic stays the same. In order to help us with that, we have a location transparency. Location transparency is a concept that tells us that a component should neither be aware of nor make any assumptions about the location of components it interacts with. Or even better, not even of which components it interacts with. So I just do not care. I want to have something done. I want to send a message. I know about the message. That is my API, and I do not care which component handles it. Of course, that cannot be done that easily, right? So if I want to communicate with another component, one traditional style is just to open HTTP connection and send it a message. This is not location transparency because I know the location. I have to know the exact host. I have to know the port, etc., etc. So what we can do is to introduce an infrastructural component. In Axon framework, of course, we have a lot of buses. I believe that our listeners are aware of those. And exactly what buses give us is this location transparency. It is an infrastructural component. It gives us a flexibility in distributing our messages. I have a reference to the message bus. I send it a message. I do not care where the other component is. The message bus knows. So what I need to do in cases when I want to change the deployment structure of my application, I extract that business logic which stays the same, and what I need to change is the implementation of the message bus. Instead of a local implementation that can communicate in a single deployable unit, let's say a JVM or CLR if we are in .NET world, then we can use a distributed implementation that knows how to communicate over the wire to different components in our system. So uh, when non-functional requirements change, again, I underline that doesn't mean that our business logic has to change. Only infrastructure has to change.
That makes sense. And I think this location transparency is key to be able to kind of go, because what we call sometimes as evolutionary microservices, right? You start with a monolith, and then with a good API design, then you can actually break up your systems as you go. And as you mentioned, Milan, really well, is that again, it's important to note that the business requirements and functionality does not change, and you can still make the so to speak design changes if you need, that are within creating this sort of monolith onto the microservices, this evolution basically happening in this case. So we use the messages, we use these message buses, we use the business and infrastructure logic, decoupling in this case that happens through that location transparency, and then we can evolve our infrastructure that way. So now, with that said, can we talk a little bit about streaming a little bit, where the components have to communicate by sending single messages and waiting for those messages to be received and so forth?
Yes, we can. When we please delete this one. So when we basically yes. Dealing with the distributed system means also dealing with latency of network communication. That means that when you are basically communicating in the same executable, the communication is super fast. But when maybe you need to communicate with a component that is deployed on the other side of the world, you have, of course, a delay in sending and receiving messages. So the traditional approach of synchronous operation that you can use, basically sending a request and waiting for a response to this request, can be very, very affected by latency, because you need to wait the full request and response process finish before to send the next command, the next request. So in order to reduce this effect on our performances, what we can do is to decide basically sending many messages without waiting for the confirmation, for the response. So we can send all the requests in a single continuous stream. And basically what we can do is to also reply, so to send responses to all these single messages or single requests in a continuous stream that flow back from the second component to the first one. And we can correlate request and response with some correlation identifier. So this is a technique that improves a lot of performances when we need to deal with distributed environment, when the latency can affect our performances.
Yeah, and of course, we are then dealing with back pressure as well, which with both of you, we did record an episode talking extensively about latency and back pressure. So that's I highly recommend the listeners to give that a listen. So, but just quickly, can we just touch on back pressure, if you don't mind?
Yeah. Back pressure basically is a very powerful technique because even if streaming, basically sending messages and continuous streaming can improve a lot of performances, we need also to be very sure that all the components in the pipe are able to handle, to respect the pace, right, of the incoming message. Because if one component could not do that, the problem are pretty obvious. So in order uh, so, to tolerate, let's say, an increased load in terms of incoming messages, a component can, for a certain period of time, basically buffer the messages that need to be handled and
Right.
to be more resilient, right? But after a while, if the load continues for too long, basically the components will end up collapsing. So, in order to avoid this, we can use this back pressure mechanism that is basically something that changes the perspective. It's not the first component that pushes messages towards the second one, but is the second one that pulls. So basically,
Ah,
requesting more and more events as soon as it is ready. So as soon as the buffer is empty enough to basically request more. So that is a technique that is very powerful when you're handling streaming, but it is not always the good solution because there are certain business where slowing down is not the best option. Better to crash in some situation. So
right.
if your business tolerate the fact that the some components can slow down uh, the pipeline, it's perfect to use back pressure.
Makes sense. Now, in cases that we don't want to basically send these messages one by one, can we optimize the performance a little bit better, Milan? Can we use something like batching?
Yes, of course. So batching is a technique that is really, really old. Whenever you need to send a message over wire, it is always better to send several messages over the wire. Because with each message, we need to have a header, we need to have some metadata attached to it, some other information. So instead of sending only one and then one by one, it is sometimes better to wait for a batch to fill and then send the whole batch. Here is really a trade-off to know how long you should wait for the batch to fill and how many messages you want to send. So in certain cases, a batch can consist of one message, two messages, or it could be 10, 20 messages, depending. If you have a burst load on your system, then your batch is going to be a little bit fuller, I would say. So yeah, definitely batching, just reducing the footprint on the wire will improve performances. Also, if you process messages in a batch way on the recipient side, it will also improve performances.
Makes sense. So, lots of great ways to um, implement these ideas if you're going from a monolith to a distributed system. As Milan, you mentioned at the beginning, if there is a need to do so, if you don't need to, don't do it. There's a lot that you have to consider. And I'm so glad that you both mentioned that not everything is technical. A lot of this has to happen on the design part of it with the business question at hand and business requirements. So that's really important to focus on because as we sometimes talk about solutions as technical side of things, we always feel like technical solutions are the best solutions, but that's not always the case, is it? We have to look at the design as well. And I'm so glad that you brought this really important topic into sort of light and shine some brighter light on it. So fantastic. Thank you both for this really, yet again, very insightful session. I always have a great amount of fun listening to you both and learning from you because this is really great stuff. So, again, I appreciate you being here. Thank you so much. I can't wait to hear more about you're doing another conference, right? Coming up in June
Yes,
Yes, we will be at DDD Europe
in Amsterdam, right?
in Amsterdam. Yeah.
Great. So, what are the dates just in case folks are around the area or joining?
So I'm not sure, but I think that our talk will be the 23. So the
Okay.
conference will be 4 days, but our talk will be one of the uh, one day between 23 and 24. I believe 23,
Gotcha.
right? Yep.
Yeah, I think the full calendar should come out soon if it's not there yet. So that's wonderful. I can't wait to hear more about that. And we also at Axon have our own conference coming up in September, end of September. And not sure if you two are speaking at that conference, but I hope you do because it's always fun to listen to you. But in any case, that conference I believe is happening September 22nd and 23rd. So that's really exciting to know, and it's going to be in person, so I'll be there, which is really cool. Anyways, thanks again. I hope you enjoy the rest of your day, and I can't wait to talk to you later.
Thank you, Sarah.
Thank you,
It's
Sarah.
great being here again.
Thanks. Absolutely. I always have great fun. All right, guys, talk to you soon.
Bye.
Thank you for listening to my talk with Sara and Milan. I hope you enjoyed it. Please join me next time as I discover other topics that are really interesting with wonderful guests such as Sara and Milan. Until then, have a great time and happy coding!